goes. So we're going to go ahead and do the notes, and we're here tomorrow, which I think we will be here useful part of the day for sure, and then maybe Thursday. A stronger possibility coming out Thursday. So we'll just go ahead and try to just get somewhere with this, and then we'll monitor and adjust from there. So polynomial functions is what we're going to be talking about in chapter 5. We'll get into polynomial functions and then rational functions as well. So polynomials are in the kind of the collegiate definition of a polynomial is you've got coefficients a sub n, so that's a subscript there, and then x to the nth power. So that's the exponent on the x's. And then as you progress through, the subscript goes down 1, and so does the exponent on the x out of that. So it's just kind of generic definition of that. And then when you get down to a sub 0, that's the constant term. So that's like the y-intercept. We do with quadratics. So we're just extending a lot of the things we do with quadratics into higher degree polynomials in the first part of this chapter. A sub n are going to be real numbers. So our coefficients have to be real numbers. So we need to keep that in mind as we'll play a little game in a second called Is It a Polynomial? And so it's not the funnest game. It's not a game show ever like that, but it's a game we got to play in class. And then the exponents on the variables are non-negative integers. That means positive integers, non-negative integers there. So positive or 0 for those exponents on the variable. So that generic definition of a polynomial is all that is. So to be a polynomial, there are certain things that you have to satisfy. One is that you have no negative or non-integer exponents. What does it mean to be non-integer? Fractions. So no fraction exponents and no negative exponents. Okay, so we've got fraction exponents or negative exponents, then that is not that expression cannot be considered a polynomial. And then no rational expressions with variables in the denominator. So polynomials do not have fractions in exponents, and they aren't fractions with variables in the denominator. Doesn't mean that our coefficients can't be fractions, just like numbers, but we can't have fractions with x's in the denominator, is what we're kind of really saying there. So no x's in the denominator, no fraction exponents, and no negative exponents on our there. Because what does a negative exponent do to a fraction or to a variable? It puts it in the denominator. So those it's kind of a redundant thing there with the no rational expressions and the no negative exponents, because the negative exponents create those things happening. So those are the only two stipulations to be a polynomial. You have to meet those two requirements. Polynomials in general have a domain from negative infinity to positive infinity, just like quadratics do. Okay. Unless we're in the context of a word problem, which we know that changes things depending on what the word problem is talking about, what the domain could end up being. But we're just, in general, polynomials are going to have a domain from negative infinity to positive infinity. Range is going to be dependent upon the polynomial, just like a quadratic was, depending on where the vertex was and what direction it opened. All of those things, depending on the equation that we have, changes the range, but the domain is consistently negative infinity to positive infinity. The degree of a polynomial, we're in standard form, which is the way most of ours are going to be presented to us. It's the highest exponent on the variable when it's in standard form. So if x cubed is the biggest exponent on the variable, then the degree is 3. And we'll talk about what that degree does and some things as we go through the chapter here. So degree, highest exponent on the variable. Make sure you know that. We'll recognize that some as we go. So here, is that wonderful game. Is this a polynomial? If so, state the degree. That's probably the title is probably why it didn't make Game Show Network because it's too long. But anyway, so here we have a function, and it's written in descending order, which is standard form for a polynomial. Is descending order. Got x to the fourth, and then x to the third, then x squared, then plain x, and then a constant. So look at the exponents on the variables. The requirement is that they're not negative and they're not fractions. Are any of those negative exponents? No. Are any of them fraction exponents? No. So it meets those requirements. Are there any fractions with x's in the denominator in the problem? No. Are all the coefficients in front of the x's real numbers? Yeah, we're good. Okay. So this one is a polynomial. What is its degree? 4. It's a 4th degree polynomial. Example B. G of x is equal to 6x to the 5th minus 5, excuse me, square root of x. So, real number coefficients, 6 and 5, those are real numbers. We're good there. Exponents on the variables. We got a 5, and then what's the square root? Yeah, what is the fraction? It's 1/2. If it's a cubed root, it's 1/3. If it's fourth root, it's 1/4. That idea. So here we have this one causing a problem. We got a fraction exponent on it. So this is not a polynomial. Because of that. So if it's not a polynomial, we're not going to tell what the degree is. All right, let's get into example C. Uh-oh. That's not normal form, standard form. I don't really have to get it in standard form to decide what's happening. I just got to think my way through it. So if I were to multiply this out, we're not going to, but if I did, would there be any fraction exponents? No. Would there be any negative exponents? No. So does it meet all the requirements for real number coefficients? Yes. So is this a polynomial? Yes. Now the harder question, what's the degree? Why? The first term would be, an x to the 5th power. That's right. Because if you multiply out x plus 4 squared, the front term is going to be x squared. And then if you multiply that times 2x cubed, it's going to be 2x to the 5th. So the degree would be 5. We'll have to multiply it out all the way, but you'll know that is what you're thinking about doing. Example D. F of x is equal to the cube root of x plus x to the negative 5 power. No, because this is x to the 1/3. And how do I fix the negative exponent part? Yeah, and so negative exponent creates this division by a variable, and we can't do that. So that's and so there are two things that cause this one not to be a polynomial. So one is enough, but this one is really not a polynomial. All right, let's do a tough one. Example E. 1/5 x to the 8th parentheses x squared minus 5. All of that to the 3rd power. I see a fraction in the front there, so that means it's not a polynomial, right? 1/5 is a real number, isn't it? And is there an x in that denominator? No, it's out to the side there, so that means that's okay. That's legal. Are there any negative exponents anywhere if I multiplied it all out? No. So that seems to fit the bill for being a polynomial. And now the fun part, what's the degree? No. If I multiply